Hi folks, starting with number 25. This is on page 414, section 5.5. After you've seen a few of these, if you've been watching my videos, then hopefully you see that square root, you immediately think, gee, I wish I could do this one. That's the one I know. So how would I do that? Well, I'd have to pick u to be that part. So u equals 1 plus e to the x. And remember, when I say to do that, it's not like, it's like because I know it, that's why I pick it. That's what you should try. Sometimes it won't work. We'll get into ones that are a little trickier that don't work, but you should still try that. That should be your first instinct at this stage if you're new to this and really trying to learn it. Okay, well, once I pick u, du it's 0 plus e to the x dx. And I'm going to substitute for everything I see. The square root has a u inside because u is equal to 1 plus e to the x. And then what I have to substitute for, that's what's remaining, the e to the x dx, it's right here already. So that's equal to du. And look at how that just turned into exactly square root of u, the integral of that. Okay, so I get u to the 3/2 times 2/3. Remember, it's divided by 3/2, which is the same as multiplying by the reciprocal 2/3. Then we'll put it back the way we found it. The u was 1 plus e to the x. Yeah, that's very standard. I'm going to take a second to just say that, you see, that's how it's rigged. So whatever you put in here for u, you need to put its derivative on the outside, and then it'll turn into square root of u. And you can put whatever you want there, but as long as you put the derivative of it on the outside, it'll turn into square root of u. So in this one, they're introducing the idea of some generalization, and this is just getting math maturity. You have to be able to deal with lots of letters, and in this case, it's kind of training your brain to see the a and the b and just treat them like a constant. They might as well be a 2 or a 3 or whatever your favorite numbers are. The x is the variable, and don't be confused or distracted by the a and the b. Okay, if it helps you, go and practice on something like dx over 2x plus 3. And then see how that goes, and then follow the 2 and the 3 around, and the a and the b will behave the same way. And so when you look at this one here, how would you do this? This is a classic 1 over u du. Okay, we'll have a little fudge factor there, but it's a classic 1 over u du. Okay, so when you have a fraction, and especially when it has a 1 on the numerator, it's a good idea to pick u to be the denominator, because then 1 over u du is one of those ones that we're expected to be good at and recognize immediately. When I pick u to be ax plus b, du is a dx. Remember, b is a constant, so the derivative of that is 0. And what I have to substitute for here is that integral. I have 1 over u, that takes care of the ax plus b part, and then I still have dx to substitute for. Dx is equal to 1 over a du. And here, this is why they say that a is not equal to 0. So it's okay that I have 1 over a. See, they covered everything. Now, 1 over a comes along for the ride. I get ln absolute value u plus c, and then the u is ax plus b. So 1 over a ln ax plus b. Any questions? I'm all alone here. I'm just doing math to the internet. All right, number 27. x squared plus 1. That's the first glom. Then we've got another glom, and that glom is x cubed plus 3x to the 4th. It'd be nice when you see an exponent like this, parentheses to the exponent, your immediate choice is to just pick the stuff inside the parentheses to be u, and then see if it works. In this stage, often it will. Let's try that. Let's see how rigged this thing is. It looks kind of random. It looks like they're just putting all these x's just to make it big and messy, but it's so rigged. Watch. If I pick u equal to x cubed plus 3x, then du is 3x squared plus 3 all times dx. Then when I go to substitute for this and turn it into a u integral, this part here is u to the 4th. And what do I have to substitute for? I still have this x squared plus 1 and the dx. And you say, well, okay, I give up, right? Where am I going to get that? Well, it's right here. Look how rigged it is. That's 3 times x squared plus 1 dx. So x squared plus 1 dx is equal to 1/3 du. And now we can proceed. I get 1/3. Like I said before, don't try to be a hero and incorporate all the fractions. Just leave it out there. Do your integration. Then we can do a little housekeeping after that. Okay, so I have 15 on the bottom, and on the top I have u to the 5th, and what was u? U was equal to this right here. I have x cubed plus 3x to the 5th. Let's see. You see how rigged it is? You see that 3 right there is put there so that when you take the derivative of this and you get a 3 out in front, that you can then factor it out and get the x squared plus 1. Very rigged. It wouldn't be as nice if there was a 5 there, for instance. So they are rigged. So rigged so that you can do them. Number 28. Speaking of rigged, e to the cosine t sine t dt. Here we have e to something, and it'd be great if I could utilize that integral that I'm so good at, this one. So if I was going to get that, or let's say u, well, I better pick u to be cosine. Then du, see how rigged it is minus sine t dt. Well, look at that. I've already got the sine t there. It had to be put there in order for this integral to work. When I substitute, I get e to the u, and then the sine t dt, this part here, is negative du from right here. So I get e to the u plus c minus there, and then put back the cosine t for u, minus e to the cosine t plus c. This is a good one to try to just do in your head. Okay, so what I would say to myself is, I want to find the antiderivative of this, but I know if I had something and I took the derivative and I got back to this, it'd have to have an e to the cosine t in it. It just would have to, because when you take the derivative of e to the cosine t, you get it back again. So I kind of guessed that, right? In my mind, I'm saying, okay, well, it's got to have a cosine t. What happens if I take the derivative of e to the cosine t? Well, I get e to the cosine t back again, just like I suspected. But then times the derivative of cosine t, which is minus sine t. You say, oh, darn, I almost got back. I just had a minus. So then that's the antiderivative. And then you'll get back to what you started with. And it's a good exercise to do that. After you finish the integral, see if you can think about it and try to do the integral in your head after you've done it by hand, if that's something you're into. If you're not a bad person. You don't have bad character. It just means you don't feel like doing math in your head, and that's fine. But some of you like to challenge yourself and get all nerdy like that, so try to encourage both sides. I think it's fine either way. Number 29. Now here we're going to have to take a little bit of a detour here, all right? Because look at how this one here is. It's got this thing in it that, well, you just don't see it that often. It's one of those ones where if you don't practice it in calculus, you'll kind of forget it. Okay, and it's related to e to the t, but it's not e to the t, it's 5 to the t. E is a specific number, 2.718, blah, 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 but here we have 5. And the derivative of e to the t, well, that's the easiest one in the universe. But when you take the derivative of 5 to the t, not exactly 5 to the t. Got a little fudge factor. And what is that fudge factor? Well, it's 5 to the t, and then you got to throw in a little ln 5. And so why does that happen? Let's actually investigate that. So the way we do 5 to the t is we rewrite 5 to the t as e to the ln 5 to the t. And now I'm hoping that you'll remember that e and ln are inverse functions. So this really cancels. This really is an equivalence. This is Robert and this is Bob. Same guy, different name. Now we also use this exponent rule of logarithms. And I'm going to bring that t out in front. So I'm going to rewrite that as e to the t ln 5. And now I'm going to take the derivative of that. So the derivative of 5t is the same as the derivative of e to the t ln 5. And how do we take the derivative of e to some gobbledygook? E to the Mickey Mouse prime is e to the Mickey Mouse again times Mickey Mouse prime. So in this case, it'll be e to the t ln 5 back again, because you always get e to the Mickey Mouse back again, then times the derivative of t ln 5. Well, this is just a constant. ln 5 might as well be 7. So the derivative of this portion is just ln 5. So I get, let's write it like this. I get e to the t ln 5 times ln 5. But e to the t ln 5, that's just 5 to the t. That's how we got it, right? 5 to the t is the same as this. See? That's Robert. That's Bob. Or maybe the other way around. So this is 5t ln 5. So remember, way back when I was starting to do this integral, I started describing how we do the derivative of this. I told you what it was, but I thought I'd take a little time to tell you why. Because sometimes things like this are hard to remember. Maybe this is harder to remember, but it'd be great if you for those of you who are trying to get pretty advanced at this, to be able to derive these things rather than memorize them. Okay, now let's get back to the integral. So when I look at this, I say, geez, I'd really love for this to be sine u. And if I were to get sine u, I would have to pick u to be 5t. So let's try that. U equals 5t. Probably going to run into space issues here. So let me erase this now. All right, and then the derivative, see how you have to have the derivative ready. All this explanation here is so that I have the 5t ln 5 ready after I take the derivative of both sides there. And that's all times dt. Now when I substitute over here, I get sine u by design, but I still have that 5t dt. So when I substitute for the 5t dt, I have to pull the ln 5 over to the other side. And that'll give me 1 over ln 5 sine u du. Now I can integrate. I get 1 over ln 5. The antiderivative of sine u is minus cosine u. And then I can put back in what u is in terms of t. So I get 1 over ln 5 with the minus cosine of 5t plus c. So let's just recap that. So I had 5t sine 5t dt. And the thing whose derivative of this, it would have a cosine, right? It'd have to have a cosine 5t in order to get back to a sine 5t. But if I took the derivative of cosine, I would get a minus, which I don't see there, so I better put one in. And if I took the derivative of this right here, I would get an ln 5t, which I don't want. I don't want that ln, right? There's no ln 5 there. So I have to have a preemptive strike and have an ln 5 sitting in the denominator so that when I take the derivative, it cancels and I get back to the original. So that's how you can reason it out in your mind after you've written it out by hand. Number 30. They're trying to get into different derivatives now to remind you of some of the derivatives that you maybe were once good at or maybe not, but it is kind of a prerequisite to be a world expert at derivatives in order to do integration. It helps a lot. That's very confusing. We've got inverse tangent, and then we've got 1 plus x squared. How do they seem related? Well, if you're good at your derivatives, you remember that the derivative of inverse tangent is 1 over 1 plus x squared. And you may remember that because it's kind of weird. You go from a trig function to not having a trig function, just a regular old rational function over there. And that's the derivative of inverse tangent. So here we have an inverse tangent, and we've also got its derivative sitting there. So how about we pick u to be inverse tangent? Then du will be 1 over 1 plus x squared dx. Well, that's exactly what I have sitting there. So that integral converts into u, and then the 1 over 1 plus x squared times dx, that's equal to du. So this is equal to u squared over 2 plus c, and then the u is inverse tangent. So I have inverse tangent x squared over 2 plus c. And you don't want to write inverse, you don't want to write tangent to the negative 2 for that. It's tangent inverse quantity squared. Number 31. Here we go. It's an old favorite. E does some gobbledygook, and then they throw in its derivative as if it's some random thing that you have to think about. But look, in order to make this integral work, I've got to have the secant squared there. And so that really shows you what we're really doing. The substitution rule is really undoing the chain rule for us. So that's why they always have to have the derivative sitting there, because if you're undoing the chain rule, then when you do the chain rule, you're going to have the derivative of the inside present. Okay, so I see a couple of things that trigger me. I've got e to something. I'd love it to be e to the u. So if I want that, my first try should be u equals tangent x. And then you just follow your nose and you get du is secant squared x dx. And then you look up here and you go, oh my gosh, this thing is so rigged. It's just so rigged. Look at that. It's just integral of e to the u, because that's e to the tangent. Tangent was u. And then the secant squared x dx is sitting right there. That's du. And it's the easiest integral in the history of integrals. Put the u back in, put it back the way I found it in terms of x, and there we go. We've got our answer. So rigged. So rigged. Number 32, again, so rigged. And look, it's the more confusing it looks, the more ridiculous with all these functions that seem unrelated. The more of them, the more rigged it is. So here, this is, you look at the way I look at it, and it'd be nice if I could coach you along to start to think of it this way too. You just go through your options. Well, I'd love to be sine u, right? Because I know I can do that. Can you do ln x over x? Well, yeah, but the ln's inside of a sine, so you know you gotta work with sine and ln. So let's try picking, because again, what I'm thinking is, gee, I'd love for this to just be sine u, because I'm good at that. And if I want that, well, I better pick u equal to ln x. And if I pick u to be ln x, well, then du is 1 over x dx. And look, it's sitting there in the integral. How rigged is that? This integral now becomes sine u. And then again, this dx over x, or it's 1 over x times dx, that's equal to du. Exactly. The antiderivative of sine u is minus cosine u. And then we put back the u in terms of x, which was ln x. Number 33, we're getting into the trig functions. Remember that cosine and sine are each other's derivatives with a minus when you go from cosine to sine. But when you see them in integrals, they usually come together, because if you're going to pick u to be sine, well, you better have a cosine there for the du. And if you pick u to be cosine, well, you better have a sine in there to be du. Now here I have a power. Remember that sine squared is the same as this. That's not how we write it. We write it with the sine squared like this one, but these are the same thing. And if I write it like this one, then it helps you see a potential u. And whenever you have a huge, think about this. You know, if you have, maybe I'll say that at the end. Actually, I'll talk about that. So let's just finish this one. If I pick u equal to sine x, then I'm hoping there's a cosine x in the integral. I'm not going to pick u equal to sine x unless I see a cosine x, because I'm going to do du, and I'm going to get a cosine x, and I better have it there to substitute for. Well, look at that, we do. So this is, geez, it's so rigged. It's 1 over u squared, and then I have the cosine dx right here. Well, cosine dx is equal to du. And remember that this is u to the negative 2 du. So if I add 1 to the exponent, I get u to the negative 1. And then divide by that very negative 1. Like I said before, don't try to be a hero with all these exponents and fractions. Just write it out the way I've done it here. And make sure you get the numbers correct. Then you can clean it up afterwards. So that's minus u to the negative 1. What's u? U is sine. Now you got to be careful here, because you can't write sine to the negative 1, right? Because that's going to be arc sine. That's inverse sine. So let's put the minus out here. And we'll take one extra step here just so you know what I'm talking about. So this is minus, I don't need parentheses. It's minus 1 over u, because u to the negative 1 is 1 over u plus c. And so then that's minus 1 over sine x plus c. See? But 1 over sine x has another name. It's also called cosecant x. So that's, I haven't looked, but that's probably how it's presented in the book. And so that's one of the challenges in calculus, is that you get your answer, maybe you got this as your answer, and then you look in the back of the book and it says this, and you know they're the same, but you do need to be a little bit fluent in your trig functions to recognize that right away. Okay, so that's the answer, I believe. Let's do one more, and then that's it. Number 34. The integral of cosine of pi over x over, you can almost, once you start to learn to build these things, you can almost guess what it has to be. And I'm going to guess for you. So because I see this inside the cosine, and I'm really hoping I can just make it cosine u, then I better have the derivative of that. Well, what's the derivative? Well, forget about the pi. Just what's the derivative of 1 over x? That's the derivative of x to the negative 1, which is negative x to the negative 2, which is negative 1 over x squared. So I expect to see a 1 over x squared. I don't have to have the negative because we can fix that later. I don't have to have a pi or anything, but there's the constants we can fix, and that's the design anyway. But I better see an x squared on the bottom, and lo and behold, there is one. So rigged. But to the non-trained eye, it just looks more confusing having that x squared on the bottom. If you're trained, you expect it to be there. So let's see what I'm talking about if you couldn't follow all that. So u, I'm going to pick that to be the inside there because I'm dying to have cosine u. That's one of the ones I know. So I'll pick u equals pi over x. Then du, remember pi is just a constant like a 7. So I have, it's pi times 1 over x. And when I take the derivative, you can just bring the pi along for the ride. I just did the derivative over here. The derivative of 1 over x is negative 1 over x squared. And now let's see how this integral transforms. I get cosine of u by design. And I still have this dx over x squared to account for. Oh, I didn't put my dx in. There it is. So let's isolate the dx over x squared. Dx over x squared is equal to, well, I've got to bring the negative and the pi over to the other side. So I get negative 1 over pi du as my dx over x squared. That's the thing I need to substitute for. So let's put it in. I have minus 1 over pi cosine u du. The antiderivative of cosine u is sine u. And then I'll put back what u is in terms of x. U is equal to pi over x. Sine of pi over x. Okay, there you go. And I know you don't have any questions because there's nobody here. But if you're watching this later, I appreciate it and hope you get something from it. And I will be back in another video.